Hello everybody. Today in this video I'm going to prove the chain rule. So most of you, when you learn the chain rule, you learn the rule, but I doubt that the professor or whoever is teaching you actually go through the chain rule. And there's a reason for that. It's much more complicated than using the chain rule. And it involves something that you usually learn after chain rule. It's called linear approximation. Okay, linear approximation or differentials. So I'm going to briefly first talk about that first, and then go into the chain rule. So the idea of linear approximation is this. So suppose you have a function. Okay. So there's a part of a function, y equals f of x. The idea of it is, okay, the function is curvy. There's different things that happen. But if we look at only a small portion of the function, right, very small part, then couldn't we, doesn't the line actually, the tangent at that point around there and the function itself, don't they look very similar? I mean, if you were to zoom this in, right, the more I zoom in, and the more you look at just the part, right, so look at this part here. They're almost the same, right, almost. There is a very, very small difference we probably cannot tell with our eyes. But there is a difference numerically. So I'm going to write that out, what I just said, as a mathematical form. So first, let me let this point of tangency, okay, let me let the x value be a. Okay, then this value right here will be f at a. Okay, so this line here has a slope of dy over dx, which is f prime at a. Okay. So let me pick a second point that's a little bit to the right of a. Okay, let's say about here. Okay, so then draw that all the way up. Okay, let me zoom in again here. And let me draw a triangle from the point of tangency to this new point. So here's my triangle here that I'm talking about. And I can conveniently label from here to here. If I label that dy, this would have to be dx, because we already know that the slope of this line has to equal to the dy over dx. Okay. Now, that's for the line, right? The line is a constant slope of dy over dx. For the actual graph, okay, so the graph, let's call that delta x. Okay, and the graph is the purple. Okay, so let's call that from here to here. It's it's almost the same as dy, but it's a little bit different. So I'm gonna label that delta y. Okay, so what I'm going to do is make dy, right, equivalent to the delta y plus the small difference. The small difference, so what I'm talking about is the small height difference between delta y and dy. So in this case, actually dy is larger. Right, so dy minus delta y, I'm going to call that epsilon. Okay. In other words, dy is equal to epsilon plus delta y. Okay. So in other words, right, delta y plus epsilon over delta x is equal to dy over dx, right? So that's a little extra thing, right? Because they have a very small difference, delta y and delta x, as delta x, approaches to 0. There's a very small difference, so I'm going to call that epsilon. And as long as that we find that epsilon, they're equal to each other. Now from here, I'm just going to isolate the delta y now. Delta y plus epsilon then is equal to dy over dx. I'm going to replace with f prime at a now. So the delta y is equal to f prime at a delta x minus epsilon. Okay. So using the idea of differentials, I've come up with an expression for the delta y and how that's different from f prime at the dy over dx. Okay. Okay, so now let's actually go to the question that we want to solve. So let me zoom out here again. So what we want to do is we want to find the formula for when y is a function of a composition like this. Okay, f composed of g. Another way of writing that is y is equal to f at u, where u in return is a function of x. So u at g at x. So writing this and these two things is exactly the same thing. Now using this differential approximation, I can say delta y, because it's a function of u, is equal to f prime at, now instead of picking a, I'm going to pick b, where b is the result of plugging in a into g. Okay, so if you put a in here, the thing you get here will be b. So I'm going to put that in there, and times by delta u, and minus, I'm going to call it epsilon 1. Okay, just to differentiate from the next epsilon I'm going to get when I apply the same differential formula for u is equal to g at x. Okay, so again, using the same formula, I get then delta u is equal to f prime at, g prime at a this time, times by delta x, right, minus epsilon 2. Okay, just note that both epsilon 1, right, and epsilon 2, they're very, very small numbers. They're small errors, and they're both are going to approach 0 when the delta x actually becomes, when it approaches 0. So essentially, delta x is approaching the dx, the infinite small differential change in the x. Okay, now I can replace that delta u with this. So let's do that. So we get a g prime at a delta x minus epsilon 2 minus epsilon 1 distribution f prime at b g prime at a delta x minus epsilon 2 f prime at b minus epsilon 1. Now what we ultimately want to find is delta y over delta x. So let's divide both sides by the delta x. Okay, then we get f prime at b, g prime at a, that's going to go away. And we have epsilon 2 over delta x, f prime at b, minus epsilon 1 over delta x. Okay, so we have an expression for delta y over delta x for the composition. So now let's let delta x approach 0. When delta x approaches 0, we get delta x is essentially equal to the dx. So this will become dy over dx, and right. So what we have here is f prime at b. Now b, I'm going to replace it with what we have up here, f prime at g at a times by g prime at a, and note that the small error divided by delta x is going to approach 0, right? Remember we discussed it here. It's going to approach 0 as x approaches 0. So that will become 0, and that will become 0. So both of these terms are gone now. And therefore we have the dy over dx of this composition is f prime at g at a times by g prime at a. This is the proof of the chain rule.